So let's plug in these smoothing methods into the ranking function to see what we will get. Okay, so this is the general general ranking function for smoothing with the collection language model. Right? You have seen this before. And now we have a very specific smoothing method, the JM smoothing method. So now let's see what's the value for alpha sub d here, and what's the value for p sub c here. Right? So we mainly need to decide this in order to figure out the exact form of the ranking function. And we also need to figure out, of course, alpha. So let's see. Well, this ratio is basically this, right? So here, this is the probability of seen word on the top, and this is the probability of unseen word, or in other words, lambda is basically the alpha here, and we have this. So it's easy to see that this can be then rewritten as this. Very simple. So we can plug this into here, and then here, what's the value for alpha? What do you think? This will be just lambda, right? And what would happen if we plug in this value here? If this is lambda, what can we say about this? Does it depend on the document? No, so it can be ignored, right? So we'll end up having this ranking function shown here. And in this case, you can easily see this is precisely a vector space model, because this part is the sum over all the matched query terms. This is the element of the query vector. What do you think is the element of the document vector? Well, it's this, right? So that's our document vector element. And let's further examine what's inside this logarithm. So we have 1 plus this, so it's going to be non-negative, this log of this. It's going to be at least 1, right? And this is the parameter, so lambda is parameter. And let's look at this. And this is the TF. Now we see very clearly this TF weighting here. And the larger the count is, the higher the weight would be. We also see IDF weighting, which is given by this. And we see document length normalization here. So all these heuristics are captured in this formula. What's interesting is that we kind of have got this weighting function automatically by making various assumptions, whereas in the vector space model, we had to go through those heuristic design in order to get this. And in this case, note that there's a specific form, and we can see whether this form actually makes sense. Right, so what do you think is the denominator here? This is the length of document, total number of words, multiplied by the probability of the word given by the collection. Right? So this actually can be interpreted as the expected count of a word. If we're going to draw a word from the collection language model, and we're going to draw as many as the number of words in the document. If you do that, the expected count of a word W would be precisely given by this denominator. So this ratio basically is comparing the actual count here, the actual count of the word in the document, with the expected count given by this product, if the word is in fact following the distribution in the collection, this. And if this count is larger than the expected count, and this ratio would be larger than 1. So that's actually a very interesting interpretation, right? It's very natural, and intuitively it makes a lot of sense. And this is one advantage of using this kind of probabilistic reasoning, where we have made explicit assumptions, and we know precisely why we have a logarithm here, and why we have these probabilities here. And we also have a formula that intuitively makes a lot of sense and does TF, IDF weighting, and document length normalization. Let's look at the dirichlet price smoothing. It's very similar to the case of JM smoothing. In this case, the smoothing parameter is mu, and that's different from lambda that we saw before, but the format looks very similar. The form of the function looks very similar. Right? So we still have linear interpolation here. And when we compute this ratio, what we find that is that the ratio is equal to this. Now, what's interesting here is that we are doing another comparison here now. We're comparing the actual count with the expected count of the word if we sample mu words according to the collection word probability. So note that it's interesting, we don't even see document length here, unlike in the JM smoothing. Right, so this, of course, should be plugged into this part. So you might wonder, so where is document length? Interestingly, the document length is here in alpha sub d, so this will be plugged into this part. And as a result, what we get is the following function here. And this is, again, a sum over all the matched query words. And we again see the query term frequency here. And you can interpret this as the element of a document vector. But this is no longer a simple dot product, right? Because we have this part. And note that n is the length of the query. Right? So that just means if we score this function, we have to take a sum over all the query words and then do some adjustment of the score based on the document. But it's still clear that it does document length normalization because this length is in the denominator. So a longer document will have a lower weight here. And we can also see it has TF here and then IDF. Only that this time the form of the formula is different from the previous one in JM smoothing. But intuitively, it still implements TF, IDF weighting and document length normalization. Again, the form of the function is dictated by the probabilistic reasoning and the assumptions that we have made. Now, there are also disadvantages of this approach, and that is there's no guarantee that such a form of the formula would actually work well. So if we look back at this retrieval function, although it's TF, IDF weighting and it's document length normalization, for example, it's unclear whether we have sublinear transformation. But fortunately, we can see here there is a logarithm function here. So we do have also so it's here, right? So we do have the sublinear transformation, but we did not intentionally do that. That means there's no guarantee that we will end up in this way. Suppose we don't have logarithm, then there's no sublinear transformation. As we discussed before, perhaps the formula is not going to work so well. So that's an example of the gap between a formal model like this and the relevance that we have to model, which is really a subjective notion that is tied to users. So it doesn't mean we cannot fix this. For example, imagine if we did not have this logarithm, right? So we can heuristically add one, or we can even add a double logarithm. But then it would mean that the function is no longer a probabilistic model. So the consequence of the modification is no longer as predictable as what we have been doing now. So that's also why, for example, BM25 remains very competitive, and it's still an open challenge how to use probabilistic model to derive a better model than BM25. In particular, how do we use query likelihood to derive a model that would work consistently better than BM25? Currently, we still cannot do that. It's still an interesting open question. So to summarize this part, we've talked about the two smoothing methods. Generic Mercer, which is doing fixed coefficient linear interpolation. Dirichlet plier, this is to add pseudo counts to every word. And it's doing adaptive interpolation in that the coefficient would be larger for shorter documents. In both cases, we can see by using these smoothing methods, we would be able to reach a retrieval function where the assumptions are clearly articulated. So they are less heuristic. Experimental results also show that these retrieval functions also are very effective, and they are comparable to BM25 or pivoted length normalization. So this is a major advantage of probabilistic model, where we don't have to do a lot of heuristic design. Yet in the end, we naturally implement the TF-IDF weighting and document length normalization. Each of these functions also has precisely one smoothing parameter. In this case, of course, we still need to set the smoothing parameter, but there are also methods that can be used to estimate these parameters. So overall, this shows by using probabilistic model, we follow a very different strategy than the vector space model. Yet in the end, we end up with some retrieval functions that look very similar to the vector space model, with some advantages in having assumptions clearly stated and then the form dictated by a probabilistic model. Now, this also concludes our discussion of the query likelihood probabilistic model. And let's recall what assumptions we have made in order to derive the functions that we have seen in this lecture. Well, we basically have made 4 assumptions that I listed here. The first assumption is that the relevance can be modeled by the query likelihood. And the second assumption we've made is query words are generated independently. That allows us to decompose the probability of the whole query into a product of probabilities of all the words in the query. And then the third assumption that we have made is if a word is not seen in the document, we're going to let its probability be proportional to its probability in the collection. That's a smoothing with the collection language model. And finally, we made one of these 2 assumptions about the smoothing. So we either use James smoothing or differentiated price smoothing. If we make these 4 assumptions, then we have no choice but to take the form of the retrieval function that we have seen earlier. Fortunately, the function has a nice property in that it implements TF-IDF weighting and document length normalization. And these functions also work very well. So in that sense, these functions are less heuristic compared with the vector space model. And there are many extensions on this basic model, and you can find the discussion of them in the reference at the end of this lecture.